Takže Zoe Laughlin, kreativní ředitelka Institute of Making a zároveň kurátorka knihovny materiálu.
Okay, thank you for having me here. I think Thomas must have said quite a few things to introduce me, but I will do it again in English so that you can get used to my voice. Okay, and then if you don't understand this bit, it's not so important. By way of introduction, I wanted to tell you that really I was like you. I went to art college and I studied fine arts and materials, and my knowledge of material science has really come from the past 7 years of doing this project. But all of my educational background was really as an artist. So my knowledge was physical. It was about making things and using materials, and really much more practical than academic. But I met 7 years ago a material scientist, Mark Miodownik, and it was very clear that we had a lot in common. We both had this enthusiasm for materials. We both had, in your pocket, a little bit of something kind of exciting, like, oh, look what I found on the beach, or look what I've got on my desk. And he had a collection of materials, and I had a collection of materials. And essentially, we realised there was a project here which was about bringing materials together and sharing them with people from different backgrounds. So it could be musicians, it could be artists, sculptors, designers, material scientists, chemists, engineers. That all of these different practitioners had a professional interest in materials, but also we all shared this similar passion to do with things. Okay, so stuff and things. These are two words that I'll probably use again, but it's all kind of synonym for materials and objects. So we began a materials library, but not only that, I started to do a PhD. So at this point we were at King's College in London, and they said, well, if you're going to be here doing this stuff with materials, you should turn it into a research project, you should do it properly. And so I now have a PhD in materials. So really the journey of the last 7 years has been about this collection, about using it, and I'll show you what we do with it. But from a personal point of view, it's been from going from an arts background, working as an artist, to really embedding more of the science and taking that understanding and then feeding it back into the art. Okay, so we have something called the Institute of Making, and the Institute of Making really is both a materials library and a home for the materials, but a space to really interrogate materials and do things with them. So we have tools and machines and a library, so we don't just collect stuff, we want to make things with it as well. And then we have discussions and seminars and do research into what materials can do and into the processes that you can apply to them. But when I started, okay, there's a test. So, no, there's not. If you ask the material scientist, like, what are materials? Generally, it's not something they would tend to define. They just kind of get on with it. And if you ask them, but what are materials? They will probably put you in the direction of this, the periodic table. Now, essentially, what I wanted to say to you today was, don't worry about the detail, but just understand this as a map. Okay, so this is essentially all of the known elements in our universe mapped out according to their properties and how they relate to each other. But it's an ideal. It's about the concept of stuff and those fundamental building blocks. But actually, once you start to get into the world, if you took something like element 29, copper, Cu, well, there's this ideal state of copper, but actually in the world around us, you might have a copper spoon or a copper tuning fork. Now, we can all see these look different. They're both made of copper, so they have this relationship to the ideal state, but actually this one has oxidized, so this one's reacted with its environment, gained some oxygen, and has a very different visual colour to it. And this one's cleaner. They're in different shapes. They will behave mechanically different. If I bend them, they'll do different things. And then they have different functions as objects. This has a clear function, right? But this has a function too. So they're both very simple objects, one material, one simple shape, but doing very different things in the world, but both have this sort of ancestor heritage of copper. Anyway, we'll come on to this. So this is the idea that you combine these materials together and you get all the stuff around us. But the other very important thing to the material scientist and to all of us really is this idea of scale. That inside materials there are structures which we can't see but that are affecting what it's like. Okay, so if I hit this tuning fork and listen to it, for the camera, and later you can hear it, it makes a sound, okay? Obviously, it's a tuning fork, but when I hit the steel one, actually, in fact, even in the room, that first sound is different, and then very different pitches. That's to do with the structures inside the materials and the relationship between its density and its elasticity. So it's how much it will move and how much of it is to move. But essentially it's all to do with structures inside that we can't see. So culturally, we're now quite used to this idea in biology. Can you understand me okay? Am I going too fast? It's okay? Okay. Too slow?
No.
Okay, so in biology, which is the left side, this side, we are kind of used to this idea that if you zoom in, and you zoom in, you zoom in, you start to see other structures, and that those structures have a relationship to each other. So actually, if you took the mouse and you zoom in, you might see a flea on the back of the mouse. You zoom in again, you see the hairs on the flea, and you could go inside the mouse and start to see tissues and structures, and all the way down to the DNA. Okay, but we understand that that DNA is code. It's an instruction, and it's an instruction to tell the structures to grow in specific ways and do specific things. So in the DNA in my body, it says grow ridiculous dark curly hair, and it tells my body to do that. And I can affect that in mechanical ways or in chemical ways, but it's in my DNA. So if I was to take heat, I could straighten it. If I was to apply chemicals, it would chemically straighten it in a different way. So I can affect those structures, but there's a relationship, what we would call the macro and the micro. The macro kind of being our scale, the human scale, and then that micro being down inside. And they relate to each other. And if you have damage, let's say at one scale, actually it will affect the story of the chain. So I might be exposed to some radioactive materials. And actually what it's doing is it's deforming and changing those structures, changing that DNA, giving new code which will then say, grow a tumour. Okay, and so then something different will happen up at the macro scale and I have a lump or something. I mean, hopefully not. But the point I want to get across is that the same thing is happening on the inanimate side, on the non-living thing in the world of materials. I mean, we are material, okay, flesh, bones, what have you, but in the sort of traditional world of metals and polymers and glass, ceramics, there's a similar story to be told about the structures inside affecting what it's like. So the material scientist, a very good example is metals. Okay, so there's a whole family of material science called metallurgy, and the metallurgist has a very ancient tradition. I mean, we were extracting copper from ore millennia ago and making things with them. So it's almost a craft heritage, our relationship with metals. But it developed and developed and developed to such a sophisticated point that it's now, a very clearly defined area of science. But really, the fundamental thing that I want to get you to understand today is that inside metals are crystals. So all metals are crystalline, basically, and that essentially means that when you zoom in, there's structures inside, and those structures have an effect on what the metals are like and what they can do. So when a metal is liquid, when it becomes a solid, that's crystallization. So when crystals grow, they kind of grow like Christmas trees, like this kind of shape. So you're having the molten liquid, then it will start to have these points of crystal growth, and there'll be nucleated, and they'll grow, the crystals will grow, they touch each other, another crystal grows, touch each other, another crystal grows, touching each other, until you have these crystals with the boundaries between the crystals. So actually that's what you can see in the middle image just there, is crystals of different sizes. So this is probably an alloy with big crystals from one metal and small crystals from another. And what that will mean is that's a material which probably is quite strong, but when you bend it, it's not ductile, it won't bend, it will be very stiff. Because if you engineer the shape of those crystals, get them to grow in different shapes, you can affect how easily you can bend a material and what it will do. But those crystals, those boundaries between, so they'll slide like this. So for me, you can all have a go at this at the end, but this metal is tin. So this is a pure element, SN on the periodic table. Tin, would you say? Tin. And what this essentially does, which I find, revelation, is that the crystals inside, when you bend it, they slide over each other, but they don't go smoothly. They kind of go like this. And you can hear it. It kind of goes, okay? And when it happens, you can feel it in your hands. You can feel the vibrations, and it feels like it's cracking. It's like, and you think, oh, it's going to shatter like glass. You can understand those are the vibrations of something very small wriggling about, and maybe it's going to shatter like glass. But actually, it's a ductile metal. It's not glass. So it's simply the internal structure, that micro properties giving a specific macro effect. But I'll have a go at cracking it now, and maybe we can hear something. But this will be something for you to do next to your ear later as well. But maybe I'll do it from the microphone as well. So.
Yeah, we can hear it.
Yeah, I'm going to come up the side. Ready? Yeah. Up the side. Okay. Ready? Yeah. Kind of crispy, crunchy kind of sound, like eating crisps. Or you maybe say chips, but yeah, eating crisps. So that's the crystals inside that material. They're really there, honestly. So just to quickly change to show you it's in all metals. I mean, here we have aluminium, right? Microscope. Dark hairs, growing everywhere. There's the DNA, what can I say? Yeah, look, Don't put that on YouTube. It's okay. So, I now put this on the microscope, you start to see these little grains, little granular structure, which you obviously can't see with the naked eye, but it's there, there's these grains. And then here we have a piece of aluminium where we've cooled it very slowly. So when it solidifies, if you do it slowly, the crystals get a chance to grow big. And these crystals are very big, and you can see them with the naked eye. Okay, so you can pass this around and just see those crystals. And what you see is it was also extruded. So that's when you take a material and you push it through a hole, right? Like toothpaste. Okay, you extrude toothpaste out of the toothpaste tube. This is kind of similar. So the aluminium is extruded, and you can see the crystals have aligned themselves in a specific direction according to where they're being pushed. So that's, the grains of aluminium. And they're really big, okay, because you can see them, you understand that. But what I want to show you now is a massive metallic crystal. So this is one whole metallic crystal. But as an object, this is a jet turbine engine blade. So, okay, let's start at the beginning. You know when you get on the plane, you have the engines under the wing, and they've got the very big blades at the front, and you see them, and you think, okay, that's going to spin round and we're going to go forwards. But what happens is they're there to gather the air. So when you're up at, thousands and thousands of feet, there's not a lot of oxygen. And the engine needs oxygen to work, to have an explosion. So those blades, they gather lots of oxygen and they compress it down and they move it further back in the engine. And then in the back of the engine, they have these around like this to make a blade, and then rows of them, so with these. And you inject fuel, and you have the oxygen, and you ignite it, and you have an explosion. So, and you go forwards. So that's a jet engine, okay? But very, very, very simply. But the thing is, think about those conditions. That's incredibly hot, and there's a lot of pressure. These are swinging round and round and round and round really very fast, so they want to pull. So there's a lot of strain on the object, the centrifugal force, but also, it's in an explosion, it's in a massive temperature. This is incredibly extreme conditions for any material. And in designing jet engines, what they found was that actually you tried to make this out of steel or something. They just don't do the job, they fail. And one of the ways in which they fail is that those crystals, that line which helps it bend and move, that grain boundary, as it's called, that line is a crack. You have a material with inbuilt failure points, inbuilt cracks. So essentially, it can just explode. So what they need is a metal with no boundaries, no crystal boundaries. So what they came across was this idea of growing this object. So this is a metal which has been grown, and it works by having it in a mould, and it's cooled very slowly with some pressure from this point, and the crystals start to grow. So they do that Christmas tree thing that I just explained at the beginning. They grow, and they hit this helix, and they grow around the helix. And then there's a kind of situation like the sperm and egg fertilization, kind of where essentially one crystal wins the race up here, and it blocks the path, because it's growing and twisting like this, it blocks the path for the other crystals coming behind. And then that one crystal can solidify this whole area. So you cut this bit off, choop, and then there's your blade and you put it in, and it's just one whole crystal without those boundaries. Does that make sense? Some people are like, yes, others are like, oh, I don't understand. But
did you say what material is it? What metal is it?
This, as a metal, it's an alloy, so a mixture of about 9 different materials. I can't remember the list, but it's simply called a super alloy. Because when they developed it, it was like, it's super. I mean, that's it. It's extraordinary. So it's just super alloy. And as a material, it's made for this job. It's made to do this object. It's not like I'm going to have a super alloy spoon. I mean, you grow it in the mould to do this job. That's it. So it's extraordinary. But if you think, it's not just a story of material science. I mean, this is hundreds of people's PhD projects, It's to get to this one state. But actually, it's our civilization's relationships to metals and what we can do with them and how we can engineer materials to make sophisticated objects. And it's also a kind of cultural object, right? You can fly because of aerodynamics and lift, but you can fly fast because of jet engines. And so you can get to New York in 8 hours rather than 8 days by boat because we can fly with jet engines, and that's only possible because of these. So, next time you're in the plane, just have a look and think, there's really sophisticated material science going on in that wing. Yeah, so anyway, that's some idea about scale and zooming in and materials. There'll be more. But the other thing, okay, this is not going to show. We're having some problems with films, but I will quickly show you on another one. Hold on. I'm just having to play this off YouTube so that... Okay, so this is silly putty. This is this material. But here you're thinking, oh, it's like a liquid. I'm just tipping a liquid onto the floor. It's like maybe cake mixture or something. It's quite gloopy, viscous. But this is actually 5 hours of footage condensed to like 20 seconds. So this this material just moves very, very slowly and you can't perceive it. And so really, I wanted to introduce this idea of time into materials. So as I said, we've got the sense of the 3 dimensions of space, but then there's the 4th dimension of time. And lots of people, at art colleges do time-based work. You're using cameras, you're interrogating the idea of duration and how things change over time, which is completely pertinent to materials. I'll just show it to you again because it's quite nice. But so this is a very big amount of time condensed down, and you start to see how materials change over time. But as I said, so back just to the idea of copper, we know this is true for all materials, right? This is not a special case. Everything will change over time. This copper will go from being very bright to being dull. Something like iron will rust. The wood will get marked and wear away and generate patina. Things aren't what they're like now in 10 years' time. And it can be in a building or it could be in your home. But other things, so certain things change very quickly and certain things change over a long period of time. But really within the materials library, we wanted to celebrate that idea and not only have a collection which was understood something, material science, but really understood materials from this cultural idea and this idea of the duration of their life, and that actually when things break, we keep them because that tells you what it's like to break it. We'll come on to some of those ideas of breaking things. Oh no. Okay, so then there's the other aspect of time, which is when you take a very short period of time and you slow it down. So this is half a second, basically. A very, very small amount of time captured on a high-speed camera and then stretched out. So I became a bit of an expert in breaking wine glasses with sound. And this was one of the things I performed this at the Tate Modern Gallery, for example, and looking at sound and materials. But really what's fantastic is this shows you about glass, but it shows you about glass when it's in a specific shape and where the weaknesses are. So if we go back... Oh, timing. Oh no. It doesn't like this, does it? We'll just let it happen. Okay, so essentially there was a moment where let's see if I can get it to go back. Come on, work with me here. It's nice though, yeah. It just doesn't want to do it until maybe it has to finish. I don't know. But what I wanted to try, I'll try and hold it on the point I mean. At one point there's a crack that goes straight up from the stem. Oh, we'll come back to it. We'll let it finish. There's a crack. You have the glass like this, and then the stem coming down. And this is the weak point because it's the join. And essentially, the crack goes up from here, and half the glass falls away. So the more I did with these, you have all the broken pieces, and you start to see the pattern. We've got one where only half fell off. It's completely in half. Another where half, but there's this. What's repeated is that failure point. And so it's actually a revealer of materiality. It's a revealer of the nature of the material, but also of the properties of this object, to have this idea of damage within the collection. Okay, let's carry on. So yes, we essentially started to make this collection as a way of having materials as a language, physical objects as a way of having discussions with people and recording some of the fantastic stories that are kind of embedded in these objects. So we built this materials library just to give you a sense of the old space. It's kind of, imagine a science laboratory, art studio, come garden shed, that kind of, somewhere where you can make things. But for me personally, it was in reaction to things like this. This is the kind of objects that manufacturers send you when you're working with materials. So maybe you're an architect and you get your swatch, or you get sent these samples of things. And so this is a kind of common sight maybe in art colleges, in your resources, and these are great, really helpful, lots of materials all at the same time, and they're kind of sort of sexy, isn't it? It's like, yeah, I've got my materials on a chain, and they're all the colours you could possibly want, and it's like, yeah, materials. But actually, very quickly, I thought, these are so arrogant. They're like pretending this is all you need to know. I need a great big bit. I need a very small bit. I need it in a different shape. Like, this isn't enough. I'm not getting enough information. So I started to make objects so that to try and understand what you could do with materials instead of just getting something from the manufacturer, asking for it, first of all, in a specific shape. So the very simplest starting point was that I said that I made and asked other manufacturers to send me the material in the shape of a 4 centimetre cube. So you can see some of them on that bottom shelf there. So this is a form which you can hold in your hand, but instantly it's not a tile, or it's something more tangible. And suddenly you're comparing exactly the same volume and you think, oh my God, that's incredibly heavy. Wow, this one's very light. And you start to have enough stuff to understand that. So again, this was what formed part of my research in the PhD, was making these sets of objects. But, so for example, we've got tungsten and aluminium, 2 pure elements, one very heavy, one very light. This is the lightest solid in the world. So this material here, okay, so this is a material that was sent to us by NASA from their Jet Propulsion Laboratory. And they developed this material for catching stardust, basically. So it's incredibly poetic. It has this extraordinary story to tell, which is that it goes up into space, is dragged behind a comet. So there's a comet flying around it, there's all this dust flying off, and the dust that's flying around in space lodges in the material. They bring it down and they look for maybe new elements or something, but they want to examine the materials up in space. But what this is the lightest solid in the world, although there's now some contention over that. But this is 99.8% air, so it's only 0.2 of it is the stuff, and that stuff is silica. So this is a kind of glass, essentially, a foamy glass. And can you see the blue colour? It's not so easy if I put it against there, but there's a kind of blueness to it. And that's blue for the same reasons that the sky is blue. Okay, so this is blue to do with the way in which the light is scattered as it passes through it, not to do with absorbing and reflecting. So this floor is blue because it absorbs certain wavelengths of light and reflects others, and those others are in the blue spectrum. But here, the light passes through it and it scatters it, and we perceive that new wavelength, the scattering, as blue, and that's called Rayleigh scattering, and that's why the sky is blue. Because what this is it's a foam. So imagine like an omelette, essentially. This is made by starting with a liquid and putting it in a sophisticated kind of oven, really. And the liquid evaporates out, and what you're left with is a foam. And the pores of those foams, so the holes, are on the nanoscale. So incredibly tiny, tiny pores that scatter the light. But when the dust hits it, the bonds between those pores can also break, and that's why the dust lodges in it. So other materials, if dust hits it, the dust will just bounce off, or the dust explodes, or the material breaks. But here, the material can kind of catch the dust and then remain whole. But it's, really very beautiful, and there's some here for you to look at. But we asked again for a very, please NASA, please make me a 4 centimetre cube. And amazingly they did. So this is the cube, but of aerogel. I also made cubes of white chocolate, or different foods as well. So this is white chocolate. So I made chocolate of 90% cocoa, 75, 50, 40, very cheap, 20, very cheap, and then white chocolate. And I came in one day and I found the white chocolate cube like this, and there was like bits of crumbs on the desk. And I was like, oh my God! I mean, I thought mice. Mice. What would you call mice? Yeah. And mice have been eating the white chocolate cube. This is a disaster. But then I began to think about it, and I was like, clever mice. This is telling us a lot about the material and also the shape, so the material and the object. This is telling us that out of all of the foods I did, this is the highest fat content and the highest sugar content. This is the best for energy. So why, the mouse is not going to be interested in the sophisticated 75%, Venezuelan dark chocolate cube. It needs energy. It's a mouse. It's got work to do. So it's going straight in and it's eating the white chocolate. But then you think to yourself, it's not only eating the one with the best calorific value, it's and the strongest smell. Look at how it's eating the cube. Okay, so imagine you're a mouse. You've got a big cube here. I mean, only as an idiot mouse starts to eat here, right? You don't go into the flat bit. You go for a corner or an edge, don't you? Because you can get your teeth around that. You go on that edge. And so that's what it's done. It started to work the edges and the corners, and it actually turning it into a sphere. And this is the thing with the selection of the cube. It has mechanical properties to it in terms of weak points. In terms of, if you take a cube, those weak points are the corners and then the edges. If it's going to chip, it chips on a corner or an edge. And when you have materials which are soft, they actually start to round off at the corners and the edges. So actually the cubes are sort of slowly turning into spheres, depending upon how easily you can damage that material. So it's just really nice to see that the mouse obviously knew this. But then I started to make still objects made of one material, but with more sophisticated shapes. So really shapes that told you more about what the material could do and what it was like. So that's some of them, and here's a few I've brought with me as well, of the tuning forks. Really, as I mentioned before, keeping the shape exactly the same, but changing the material. So this idea of a swatch being kept constant, but that actually that object performs. It does something to also reveal how the material performs. So you have this relationship between what the material can do and the function of the object coming together. And then within the collection, you can physically interact with them and have that experience. The next thing, we also made bells of different materials. So here's 3, but we have a glass bell, and we also made a mercury bell. But the mercury bell it lived in the freezer, because obviously mercury is a metal which is liquid at room temperature, so it has to live in the freezer to remain as a solid object. But actually there was a power cut, and so the mercury bell is now a puzzle. But from bells we did glass. So these are objects that really give a very loud impact. Then we started to interrogate taste. So these are really aspects of materials which we call the sensor aesthetics. Maybe I can write that.
Sensor aesthetics?
I'm not very good at spelling, but and seeing as we invented the word, I should be able to spell this. Or was it the other way around? Yeah. So you've got aesthetics, so the kind of characteristics of what it's like. Aesthetics, yeah. Public spelling is very pressurised and censored, okay? So it's to say that aesthetics, generally people consider aesthetics as being about what things look like, right? Whereas actually we wanted to develop a sense of understanding all aspects of materials as we interrogate them with our senses. So what does it feel like? What does it smell like? What does it taste like? What does it sound like? And what does it feel like? And so it became clear that the collection was doing that, and that we could start to research those properties. And so the tuning forks became a way of really researching what materials sound like in a way that material science hadn't done before. So often in material science you have very abstract shapes, and they're put them in machines and they'll break them, and they record data, and they'll extrapolate out from that some sort of equation that means stiffness. But the equation that means stiffness always takes away whatever shape the object was made into in the first place, because the shape is not important. They just want to know the stiffness of steel, not the stiffness of a steel girder in the lab yesterday. So it's got to be much more universal. So the idea of picking interesting shapes was relatively new, and we started to use these forms as ways of testing things. And it really culminated in the spoons project, where we used these spoons to test what materials taste like. And we ran a series of experiments using human subjects, and they were blindfolded and asked to taste the spoons and then rate their perception of them. So how bitter it was, how sweet, how salty, how pleasant, how unpleasant, and how strong the taste was. So different adjectives were used. And then we took those results and we see if they map against something that we can measure scientifically. So how reactive is a material? So for example, is there any correlation, any relationship between, if everybody says, oh, the copper spoon is really, really bitter, does that then coalesce with copper also being very reactive? And does bitterness and reactivity always match together, this kind of thing? And we really found there were some good links between people's perception, their agreement on what they tasted like, and what the physical characteristics of the materials are. And we published 2 scientific papers, the first just about the spoons being eaten, and the second being about eating yogurts of different flavours with the spoons. But it didn't end there. I then started working with a Michelin-starred Indian restaurant in London, and we designed a menu to use and a meal that used the spoons. And about 3 weeks ago now, we had a meal with Heston Blumenthal, who is a chef who does a lot of that kind of science of cooking, gastronomy, molecular gastronomy type work, and has, I think himself, 3 Michelin stars. And then a food writer who's kind of the world expert on science and cooking, who's written this ginormous Bible on science and cooking. And we had a meal with these different experts where we used these spoons and we started discussions, and now we're working with manufacturers to make a set of bespoke spoons that people can essentially have at home and use with different foods and have this experience with. So it's sort of gone from us in the lab playing about, making, breaking, tasting, licking it, oh, Martin, put that away. That kind of, the playful side of things, where you think, actually, there's something there, where we do the research, we do a series of experiments, but then we have a sort of scientific output, but actually there's still this design, real-world, human aspect that we're interested in, so we take it to the meal and then, disseminate the work out in the real world as objects. So that's sort of one way in which our research gets out there, and we have this collection which people can come to, but we also stage events and exhibitions and put on things in the public domain. So just to give an example, we had an event we've done a series of work with the Tate Modern, but one specifically involved them giving us the gallery space for a series of evenings where we made new pieces and we brought them into the gallery and then put them on display, essentially with the sort of the raison d'etre of please do touch. So if you go to a gallery and it's always like, please do not touch. And I'm like signing up and touching it. And sorry, no. And you go up and you always want to just, because it's just so tempting, isn't it? Like, what's that like? You want to touch these materials. And we thought, well, let's put on a night where everything is there to be touched, but not only touched, kind of could be destroyed. And so an example would be the silly putty. We made a ginormous amount of it, and we put it in the middle of one of the gallery spaces, and it was in a room with Francis Bacon paintings around the outside. So there's sort of these images of contorted flesh, and then this sort of flesh-like material in the middle that people could touch. And actually, through the course of the evening, there was the usual kind of prodding and poking and banging and stretching, but it bounces, by the way. Anyway, they also rolled it out into a sausage, and the audience just, made a huge sausage that stretched through the whole gallery. But for me, it was really interesting because you do these things in art galleries as an artist, and you have to occasionally apply for funding, say, and they always want to know how good it was, and they ask you to provide feedback on your grant, or I'm doing a PhD. I should do some measuring of how good it is. How can you measure? I mean, it's ridiculous. But anyway, there are ways and means. But I thought that it would be a great idea, again, to work with this idea of damage as an understanding how people interact with materials. So at the beginning, we weigh the silly putty, and at the end, we weigh it. And so the amount missing is an index of how much people liked it. because you don't steal it unless you really want it, right? And so nearly half of it disappeared. And we never told people they could steal it, but you pull a bit off and you saw people wandering around. Don't do it later, but we saw people wandering around, holding a bit in their hand, and then slowly it just makes their way into the pocket, and then you've got it. But for me, that means it was a success, in that, as I said, you don't take something unless you kind of have formed a relationship with it and you like it. So instead of saying to someone at the end of the evening, we come up to them and we say, "Oh, now please fill out this feedback form to tell me how much a good time you're having," because the minute you do that, you don't have a good time anymore, right? It's like there's in science there's something called the Heisenberg principle, which is about the measuring of electrons, and it says if you know where an electron is, you don't know where it's going, or if you know where it's going, you don't know where it is, because in measuring it, you change something about it. And I think a lot of what we try to do when we measure experience is we change the experience, because so I wanted to try and understand how we could measure through materials experience and just ask the material, so what happened to you? Well, you've clearly been gripped and twisted and stolen. So we can understand something. It's kind of like a almost forensic science-esque way of looking at materials versus people questioning. Anyway, that's this kind of sidetrack, but I like it. Another thing we did was, there's a work in the gallery by Jeff Koons. This is the piece on the left, which is called 3-Ball Equilibrium, and this is 3 basketballs in a tank of liquid, and the balls are at neutral buoyancy, so they're neither floating and bobbing on the top or sinking to the bottom, they're just there. And in fact, you come in every day, they're in a slightly different position, because they're not like in a resin, they're in a liquid and they will move, but they're just floating. And this is a fantastic state to be in, as it were, this sense of neutral buoyancy, neither floating on the surface or sinking to the bottom. And we thought it's quite interesting to try and make it, so we filled balloons with helium, very large, about this sort of size, and we had string kind of twice the height of the gallery, and then we had some blue tack material a bit like this, and we allowed people to essentially try and make neutral buoyancy themselves. So how much will I need to put on the string of the balloon so that when I let go of the balloon, it doesn't go whoop or fall to the ground. So you're trying to balance the forces to just make these things stay in midair. So people started to make them. And in fact, they started to take some of our cubes and tie the cubes on, and we were like, well, this balloon is like 1 balsa wood, 2 oak, and this kind of thing, different materials. But it just as various things. So we did a lot of, 40 pieces over the course of a month there. And then the Tate commissioned us to make a podcast, which was a kind of record of the events, but also a new idea, essentially, to try and do a tour of the gallery, looking at the materials from which things are made. So we got to go up to some of the paintings and kind of scratch them and look at what sounds they made and look at acoustics, as well as just have conversations about the materials. But one thing, you can get it on iTunes. But one thing that was great that came out of it was that there's a piece by Manzoni, who's an Italian artist, long dead, but who essentially made a work called Artist Shit, and legend has it that basically he pooed in a can, and I think there's 6 of them or something in the world, and inside this can is artist shit, and that's the artwork. And the idea is he never told anybody if it really is or isn't. It's just a sort of title of a can. So there's this whole question of, is there poo in the can? And we were allowed to kind of investigate. I couldn't believe it. I mean, I said, can we do some tests to see if there is shit in the can? And I would have thought that the Tate would say no, because if you find out, then you change the proposition. So anyway, they let us. So here's Mark and Martin, the other co-directors, and we were able to get access to this can and do a few swabs and look at it under UV light. And under UV light, you can see there's kind of organic matter glowing around the edge, so something organic's in it. But the best thing was that in fact, it was Martin, I think, who did this first. But he just picked it up, And then whilst everyone was sort of like, he was just looking at it, and then he shook it. And if you think about it, I mean, if I shake this, there's a sound. You know, things inside containers will make specific sounds. And I'm thinking of a poo in a can, it might go dunk, 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 dunk. But this didn't. It went chick, 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 chick. And you're thinking, oh my God, it's loose. I mean, it sounded like rice or sand or something in a can. And you think, oh my God, well, it can't be shit. But then you think, well, actually, let's think about the processes. Let's think about the relationship between materials and processes and making. If you're going to make a poo in a can, how do you do it? And actually, if you put in wet poo and seal it, you've made an environment where there's bacteria and they will anaerobically respirate, so they'll get up to stuff and they'll start to produce gas, and the tin will swell up and the tin will explode. So you don't want to put in fresh poo. What you want to put in is dry poo. So maybe you're in Italy, you're an Italian artist who's going to put your poo in a can. You put them on the wall in the sun in the summer and you let them dry. And then you put your dried turd in a can and seal it. That's going to be fine. But then if it's dry, actually it's going to be crumbly, and over time it might well become loose. So you think, actually, that's maybe more of an argument that it really is poo in the can, and then with that organic thing around the edge. So we kind of think it is, basically. And that there's a podcast that will explain that. But these events were really very successful in London.
London is weird, I would say.
Yeah, we're British, we like bodily things. Anyway, the poo jokes. There's a gallery called the Wellcome Collection that have a whole string of exhibits that are about the body and well-being and health and things. And they were reopening their space, which is sort of a museum of old medical instruments and curiosities, and then a modern art gallery. And they asked if we do, like we did at the Tate, bring materials in, have this evening where people can come and touch and do things with materials. So we went around their gallery, and it dawned on us that this was all about the body, and yet there wasn't any of the material of the body really there. So we would do an evening about flesh as a material and really look at everything from figs. Well, let's see if this will work, but I think we have to go to the YouTube. So this is a fig, by the way. So the fruit,
Fig?
Yeah.
Did you say
Fig.
Yeah.
Yeah. Say fig. Okay, so that's the flesh of fig. But anyway, we had these tables with different fleshes on, but we opened with this guy. This is Troy Brown. He's a British heavyweight bodybuilder champion. Okay, so he's won all sorts of competitions. And he's an expert in building muscle, okay? He's an expert in developing flesh in a very specific way, making very specific shapes, knowing what actions you want to do. So he was there, you could touch him, he could lift you up, and he showed you all the food he had to eat, this kind of thing. We had a butcher who bought different cuts of meat and different organs from animals. So you could really see how the material of a liver is very different from the material of a lung. A lung is like a foam, very spongy, whereas a liver is completely different. So you can see here he's cutting some liver. But also looking at different knives, how different knives will cut material. Here's a ceramic knife. But people actually didn't have to wear gloves, but they tended to choose to. But you can imagine there's a bit of a health and safety nightmare in getting all of this approved for people to touch, but we did. And it was a really extraordinary evening. You suddenly realise the smell of these things. I mean, in this more museum space, they had these old surgical saws, the reality of which is for doing this, right? Cutting through a bone. What's that really like as an action? How hard is bone? So we managed to have different types of saws for people to try, but also drills for teeth. So we had hand drills and electric drills and these jawbones of sheep that you could, attempt small drilling actions on. In this space it all had to be in these boxes because it had a very controlled atmosphere in the museum, so we couldn't release things into the space. But here is sinews and tendons and ligaments and elastic bands. So you're looking at the kind of the man-made elastic object and then the natural elastic object within our bodies. And really you had Newton meters, and you could go either end and pull them with people and really compare how the two materials reacted. That's my sister. So this is the Gunther von Hagen, and the German guy who plastinates these bodies. There's a slice, and next to it we just had cold meats, you know, bacon and what have you, and people could eat it. And it was really to look at the similarity of that material, like a thin slice of human is not so different from a thin slice of pig. Here we had women who specialised in waxworks for the police or for medical things, kind of like Madame Tussauds, but when they want to reconstruct someone from a skull, or they want to make likenesses, and she was there looking at the mimesis of flesh. And then this activity was great. We had some retired plastic surgeons who ran a suturing class. So this is pig skin, and you could cut it and be taught how to sew it up, which was, fantastic experience for people, looking at the different ways, the different types of cut and the different joins you would do to make invisible scars, or to do a facelift, this kind of thing. But so this was flesh. You get the idea. So, where are we now? Well, we are moving into this new space, which is 10 times bigger, really, which will have this extraordinary materials library at one end, at the back, this incredible workshop, and a kind of space in between for making, doing, presentations, the whole thing. We continue with our research, and we're making an iPhone app that will really be an interface for the materials. So within the collection, you'll be able to go, oh, what's this one, and look it up on the system, but then outside it will be free to everyone to interact with. So there's the materials library. And then really I just wanted to end by, again, talking about more of the things on the table, showing a few images and allowing us to kind of have a discussion, really. But some of the things you have seen already. Okay, so how are we doing on time? That's a sort of hour of me chatting on. I can now talk about sort of a few things on here, or you can ask some questions and do this at the same time.
Shall we not get here closer?
Do people want, maybe, come and everybody is all spread out. Yeah. Who likes to sit at the front? Nobody. But now you might, because come a bit closer and then we'll do something here. Okay, so has anybody been eyeing something up specifically? And we'll be like, what's that?
I would like to hear the noise of the different
tuning forks.
Yeah.
Okay, so to compete with the music school. So that's steel. That's producing a frequency of 440 hertz, which is an A. Basically, this is what the orchestra would tune to.
Can you do it once again?
Yeah, let's just close the windows in a minute. We'll all suffocate, but it'll be a bit quieter. Okay, I'll try it on this table, it might be better. Okay, now we'll compare with the copper, because I was talking about the copper. Now, maybe you just there? Okay, so what we'll do is we'll pass these two round. I mean, it's not baseball, so, but the way to do it is hold it on the bottom here and then just tap it. You can even do it on your own hand. And have a listen either side like that, then you'll hear the difference. Yeah? Okay, so that can slowly move through the group. But what's nice is this is brass. So this is steel but gold plated. But this will be the A. So that's lower. But not only that, it feels different as well. This is still vibrating. Okay, so the brass is fantastic acoustic material. I mean, it's no mistake really that whole sections of orchestras are made from this stuff. If you were a physicist, you might argue that actually, for the physics of an instrument, let's think of a trombone, right, is simply about the volume of air vibrating. So when you play the trombone, you change the amount of air in it and that changes the sound. But the musician would say, actually, no, there's a quality to the brass trombone with lacquer or without lacquer or versus a plastic trombone. So these different materials do have an effect on the sound. And so not only when you strike things, but when things vibrate. So we made a bugle of lead and a copper bugle so that you can really see those differences.
Can you find out somewhere on website different materials and different noises like you are showing to us here?
One of the podcasts actually has it all done in order, like you can hear the different sounds as well. But I think just as far as this one, you can listen, but just also feel how it vibrates differently when you do the brass and that one. So just, yeah, that one can pass around. I won't pass these ones because they're more fragile, but these are wood. And then wood, listen. This is not ringing, okay? It has no, sustained sound. But if you flick it like that, and then there are different sounds. So from out at this distance, it's all going to sound pretty similar. But if you very carefully just give it a flick by your ear, you can compare those two, and you'll hear their different pitches. But what was really nice in the research, we realised that it's not like all woods are very low and all the metals are very high. Actually, some of the woods are higher than metals. One of these woods going around the spruce makes a tone of frequency higher than the steel. It just doesn't sustain, so it has a frequency to it. And then you can start to think about wood as a resonating thing, wood as a sounding board that actually has inside it hard bits, soft bits, hard bits, soft bits. And they're quite like essentially tuning forks. So you've got a frequency that the wood will be more resonant at than other frequencies to do with the structure of the wood. And that's why things like spruce are good in guitars, because it's got very even grain, so it vibrates very evenly and is good for sounding boards. And this is just a polymer. This one doesn't make any sound. But anyway, that's some tuning forks. What else? Next up, who? This one. Okay. So you may have here, I don't know, do you have any 3D printers in the art college? Yeah. So this is an early rapid prototypes object. So this was, when they were very new to not even to the market really, to research, and they would work by pushing out glue into nylon dust, and then you shake off all the dust, and then you have your object. So the nozzle was glue, dust, and it would build up these layers. And this has been made like that. It's quite fragile, but what you'll see is that because when you know the technology, this has been made as one whole piece, one continuous object. Instead of getting something and joining it, this is made complete. But I wanted to just show you the old, what's on a way now, the old-fashioned material for 3D printing. And this is an ABS plastic, so this is a polymer which is the sort of the next generation really. And then here's the third thing, which is metal. So I wanted to show you the kind of already the 3 generations as I see it that this technology has been through, from going from powders and glues and quite delicate objects to something more mechanical that can work, which is the cogs, and then to really industrial parts. So this is, it's incredibly boring, isn't it? It's a bracket for some machine. But this has been printed essentially with a laser firing at the metal powder, so melting the metal in the very specific areas and sintering it into this shape. So that's the sort of 3 relatively recent iterations of what this technology can do. What next? Who next? Any picks?
I would like to ask you regarding the spoons and the paste. Which spoon has been successful for what, or what is the perception?
Okay, so these two, yeah. This is zinc and this is copper. These are very strong tasting. They essentially, are either nice or completely disgusting, depending upon what you put them with. So if you were to eat something acidic with these, it's really, like even tomatoes, like a fresh, homemade tomato soup with the copper spoon is not very nice. But actually, with other things, we found that when we used the copper with chili, so you had a dish which was very hot, the copper was quite nice. Because this has a strong taste, and a chili would have a strong taste, they kind of work well. Also, the copper is very thermally conductive, so actually it's cold, and it cools the mouth a little bit. So sometimes if your chili was too hot, we found that using the copper spoon can calm it down a little bit. But the zinc, again, for some people, it's quite disgusting and very astringent, but I found that this is a slight generalisation. This is not a sort of published scientific, researched outcome, but I've noticed that when we've done this and we've used the people who've tried it have been kind of men over late 50, 55, older men who maybe quite like beer, or the strong tasting things are quite nice, because actually as we all get older, your taste buds, you lose taste.
Is hygienisch.
Yeah. So if you can't taste, some of these are quite subtle, and children, they're like, everything is disgusting because they're very sensitive. Whereas when we get older, we don't like it. And then if you drink a lot and if you smoke, that will again change your taste buds. So some people like them because they have something to them which is pleasing. Anyway, they're the sort of extreme spoons. The chrome, we had stainless steel, which is the normal cutlery, but actually it turns out that it's quite metallic. It's not as absent as chrome. If you use pure chrome plating, that actually that has less of a taste. And then the least metallic tasting spoon of all is the gold. But not only that, this works really well with quite sweet things. It's quite it's really tasty, but incredibly expensive. So, unfortunately I didn't get a chance to make a platinum one. But the gold spoon, we should all be using gold cutlery, is basically the result.
It's the best.
Yeah. But we've found with sweetness, again, because these are so strong, it almost becomes a contrast to the sweetness, and things can taste sweeter than they really are. Like if we have a sweet yogurt and you eat it with a stainless steel spoon and you eat it with a copper spoon, you might be thinking it's sweeter when you eat it with the copper, and that's probably because you think the copper is so not sweet that it gives you a contrast, whereas there you just taste the yogurt. But so that's one of the spoon's findings. So I just want to show. I think this is good. Does any of you architecture students? No, I told them we do some architecture, but anyway, it doesn't really matter. But this is a great material, which is straight out of the research lab, but really has great implications for our built environment. This is self-healing concrete. This is a concrete which essentially can seal cracks that form in it. And so what you have inside are bacteria, and there's food for the bacteria there, but they're dormant. They're not doing anything. But when they get wet, they kind of come alive, and then they start to get to work and eat the food and do their bacteria thing. And what they end up doing is outputting. Oh, it's poo again. No. So the byproduct of the bacteria eating this food is the production of a material which actually seals the gap. So I don't mean we couldn't snap this in half, dip it in water and stick it back together, but if a hairline, a very thin crack forms, actually it would seal it up. And if you think about how cracks form in buildings, you have a small tiny crack in water gets in, and then it gets cold and it expands, water gets in, and so you may only notice the crack after 2 years, but there was, 2 years ago there was a very, very tiny invisible crack. Well, this would be, helping at that stage where you've got this very tiny crack, and it would seal it up. So you could pass that one around.
And I would like to see that massa material. and take a picture.
Yeah, I can't hand that around, I'm afraid, but we can show you closer. This wasn't even used to be do not open, but it's definitely, unfortunately, do not touch. But you can have a closer.
Let's try.
Yeah, nice try. Oh, we can't, because what happens is when you touch it, it picks up the oil and the sweat from your hand, so it goes white.
Is it okay to take a closer
Yeah.
look?
It changes colour, so you can see these white parts. That's where stuff's touched it. Or here, there's somebody's put their finger on it there. So we have a piece that you can touch, but I haven't brought it with me. There's one thing I haven't said is because we literally moved into the new space, well, in a temporary space, but the new space is open. Everything's in boxes at the moment, so. But this is where people have touched, accidentally put a finger on it. It changes the colour.
It kind of looks like bacteria growing on this.
Well,
You
the
know,
little
how
white
it's how
mould
it looks
spots.
the material itself, because you know how it makes that fuzzy layer.
Oh yeah, I know what you mean.
It's
Like
like
sort
that.
of, where the edges is
Yeah.
unclear. Yeah. This is nice. Has anybody got? Let me find that piece of paper. Let's borrow. Yeah. Thank you. Okay, so this is a rock called ulexite, which is a naturally occurring optical fibre. So, optical fibres. Ulexite. Yeah. It's basically a rock which, when light travels through it without losing any of the quality of the image that's being carried. So when you place it onto paper, you can see that with an image, it brings it to the surface in focus. So what you're looking at here is something in optical fibres. The light will travel down, and you won't lose anything with the internal refractions, and you get the same information at the other end. You get the same image, and the same is happening in this rock. But what's great is that when you see it, it's kind of becomes like a screen almost, but it's completely natural. Yeah, you can take a photo again. Yeah, that's a good one to pass around. But you need the paper to really see what, and you have to kind of look at it from above. That's nice. This is nice from an art college point of view because this is a material that is a very early prototype, but this was invented by an artist designer who essentially was looking for use for waste products. So the fish industry produces mountains and mountains all over the world of the scales of the fish. So when they come to the factory and they scrape off the scales off the skin and then they use the fish for whatever. So there's all these scales, and they found that if you compress them, put them under a lot of pressure, they become solid and they form a new material. So this is fish scales, but all that's happened to it is it's compressed, and they fuse together, and it's almost like a kind of fossilization. They become this kind of rock-like material. So there's no glue involved. It's simply compression of this, and they're finding it's very fire retardant, and it's got certain properties. So they're trying to make it into certain objects.
Is it fragile?
It's relative. I mean, it's not like you won't snap it too easily, but you can feel it's not. It's not like a metal or something.
Is it produced in
not on large scale yet, no. No. So this is essentially still at the early stages, but really come from someone's project, and they've invented this small material, and now looking to take it to market. Okay, so in this jar, we've got a black liquid, which is magnetic. So this is a ferrous fluid, which if you apply a magnet, you will see kind of spikes. So that's the lines of magnetic field coming off this magnet, passing through the liquid and kind of being rendered physical for you to see. But the thing is, please don't open it because it's very messy. But, anyway, pass it around, be careful. But what this is it's nanoscale iron filings, basically. So do you remember we were talking about the very, very small particles that the pore size of the aerogel, for example, those pieces of iron, basically like a rust, are suspended in this liquid. But if you just took iron filings and put them in a liquid and then apply a magnet, you would just pull out the metal and be left with the liquid. But what you have here is an emulsion which it actually suspends those particles, and the particles can't pass through the liquid to be extracted. So instead, the whole liquid moves, and it alters that viscosity. So it alters how easily the material will flow, and gives that effect of then having a kind of, it's still wet, it's still liquid, but it reacts more like a solid. So companies like Bentley, the car manufacturers, and I believe Mercedes-Benz are now using this liquid in the suspension of the cars. So inside the car you have a little knob that says hard or soft suspension, but what it is, it's an electromagnet, and it's being applied to the area where the hydraulic suspension is, and it's changing the viscosity of that liquid. So you have a liquid which is stiffer, and so you've got hard suspension, or a liquid that's softer and you've got soft suspension in your car. But that's that stuff. But it's something, again, you really need to sort of feel and handle. What else have we got? Something else to feel.
Would you be so kind and write on the board the name of the stone?
Yeah, the stone. Next one, yeah. I think in America, if you go on like eBay, on eBay search for that, and you can buy bits. But the thing is, because it's naturally occurring, it's not. You're never going to get a big bit. That's about as big as it gets. So there's no chance they're going to be making windows from it or something. But it's you can only get small bits, but it just does something really nice. Yeah. Do you know what I did there? Look, what an idiot.
But we got it. It's fine.
I didn't. No. So this kind of wobbly, gelatinous object here is essentially this. So what we have here is aluminium foil, which has glue laid down in strips. You put another piece of aluminium strip glue, another piece of aluminium glue, until you end up with a massive stack of the aluminium. But it's glued together at these points. So when you stretch it out, you can see the gaps. And please don't, but if you were to pull it completely, and you pull it what would be called beyond its elastic limit, so beyond the point when it comes back, it becomes like this. So this is about, half a centimetre, 5 millimetres. Not elastic, yeah. That's this. But this is then used, for example, in aircraft, because it's incredibly light, but very, very strong this way. It's not very strong that way, but you can put other materials here and build a composite, so that's a material made up of others. So you might put some carbon fibre here and here, and you have a very, very strong but light kind of building block. But what I really love is that this tells you again about that thing of the macro, micro, and the structures. So here we actually have a macro structure, a structure we've made at the human scale that we can see, but what it's doing is it's producing almost like a jelly-like wobble in the object. So the properties of the material of the whole object become different to what they are of the component parts. So the aluminium foil is not wobbly, or it doesn't feel like jelly-like, but the object then does because of that structure. This is the process to make this. So you make
use it like this.
Start with you make this in order to then make that. But this is saying stop halfway through the process. Yeah. Okay, so I think how are we doing on the time again? Just check. I think the last thing I'd like to just introduce is this material. This is a bioactive glass scaffold. So this is a material which is designed to be an implant in the human body and essentially disappear. This is designed to become animate in the sense that if it's a bone replacement. If you break your wrist, let's say, I hope you don't, and it would be like this, and you have to have metal pins and fix the bone somehow, you would actually be able to cut back to a nice flat end. You insert a piece of this material, but you impregnate it, so you have inside it stem cells and some protein, and that acts as a food. So when it's in your body starts to eat it and grow on top of it bone. So actually in, let's say, 2 years, you don't have an implant anymore, you simply have your own bone, because this has become a scaffolding for the growth of new bone in its place. But you can, don't open this one, but just have a look. But essentially you can see bioactive glass scaffold. But again, this is the sort of thing, as the collection, I mean, you can't buy this, it's not a product. This is from the research lab and the hospital who are testing it. So as far as the collection is concerned, we're really interested in those things. There's space for the things, obviously, that you can buy and the manufacturers supply and have interesting stories, but there's also space for the thing that's straight out of the research lab, that's new and isn't a product, isn't something that you can go and buy, as well as the things that are broken. I mean, this is an elastic band, but I mean, what sort of idiot wants to keep this? And this does not work as an elastic band. This is old, destroyed elastic band, but it will actually tell you what a new elastic band will be like in 10 years' time. So again, it's the story of the material as opposed to kind of the product that you can go as a designer and specify for your object. But yeah, it all sort of is valuable stories really, and talks about how materials are around us every day and part of our culture and society. But that's it really. Thank you very much for listening.